Hello everyone, I'm Takahiro Nishida from Shizuoka Institute of Science and Technology. Today I would like to talk activation energies of chloride-induced corrosion of steel in concrete. These pictures show the deteriorated concrete member due to chloride attack constructed in Manila, Okinawa, and Tokyo. These deterioration process of reinforced concrete member may be influenced by ambient environmental other than material use, construction technology, and so on. This study focuses on the temperature dependency of deterioration process of reinforced concrete member due to chloride attack as one of the remarkable influential factors in environmental conditions. Background. As our experience, it is known that the deterioration speed of reinforced concrete member increases with temperature elevation. Based on this experience, acceleration tests in laboratory or exposure tests in situ were conducted. However, there is little quantitative information of temperature dependency of deterioration of RC members due to chloride attack. Especially in the case of prediction of deterioration process of reinforced concrete member, it is necessary to construct an appropriate model or evaluation method, including temperature effect as a parameter. From those backgrounds I mentioned, the objectives of this study are set as follows. First, to investigate the influence of temperature on chloride ion diffusivity and corrosion rate of reinforced steel bars in concrete induced by chloride attack. Second, to study temperature dependency of chloride ion diffusivity and corrosion rate based on activation energies calculated by Arrhenius theory. Third, to clarify the influence of temperature on deterioration process of reinforced concrete due to chloride attack based on the predicted result using activation energies with temperature profile in each city. First, I would like to explain the result of temperature dependency of chloride ion diffusivity. You can see the testing procedure here. In this study, 5 by 5 by 0.5 mm of test piece taken from concrete were used for investigation. The test piece formed by epoxy resin was set the diffusion cell as shown here, and both of cells were filled with 3% sodium chloride and saturated calcium hydroxide respectively. This diffusion cell were exposed to air controlling chamber set at 20, 30 and 40 degrees centigrade, and the chloride ion concentration in saturated calcium hydroxide were measured every day. Then the chloride ion diffusivity was calculated by Fick's law. As shown this graph, it was confirmed that the chloride ion diffusivity increases with temperature elevation. Also, this figure shows the relationship between logarithm of diffusivity and reciprocal of absolute temperature called Arrhenius plot. From this, we can obtain that the chloride ion diffusivity follows Arrhenius theory. Here, Arrhenius equation can be expressed as shown here, and this equation can be translated to as follows. Also, we can obtain the slope of Arrhenius plot, so the activation energy can be calculated from this equation. This table shows the activation energy obtained by this study and literature survey. Right side shows the relationship between chloride ion diffusivity of concrete and water-cement ratio proposed by JSCE standard specification. And the broken line in this graph shows the chloride ion diffusivities considering with 10 plus minus 10 degree difference against JSC equation using obtained apparent activation energy. From this graph, it is observed that the scattering of chloride ion diffusivity in the literature data seems to be explained by temperature effect. Therefore, it can be considered that the temperature profile is one of the most important factors when we check the diffusion coefficient of chloride ion in design stage. Next, I would like to explain the temperature dependency of steel corrosion in concrete. This slide explains about corrosion formation of steel bars in concrete. As you know, the corrosion reaction progresses with these anodic reaction and cathodic reaction. And corrosion formation of steel bar in concrete separate to two types related to the location of anode and cathode. In the case of macro cell corrosion, anode part and cathode part located different positions, and the generation of rust tend to localize, and sometimes the corrosion rate becomes high. On the other hand, the anode and cathode uniformly distributed in the case of microcell corrosion. In present study, in order to separately evaluate these corrosion formations, divided steel bars are used. Here, divided steel bar consists some small steel elements, and the neighborhood steel elements are connected by non-electrical conductive epoxy resin, and these elements are electrically hooked up by the lead wire. Using this divided steel bar, we can obtain macrocell and microcell corrosion rate separately. This slide shows the temperature dependency of macro and microcell corrosion rate. From this graph, you can see that the both corrosion rate of steel bar in concrete increases with temperature elevation. Additionally, the macrocell corrosion in concrete relatively higher than that of microcell corrosion in those experimental cases. And those graphs show the Arrhenius plot of corrosion rate of steel bar in concrete. From those results, it can be said that both corrosion rate apparently follows Arrhenius theory. This graph shows the relationship between activation energy and concrete resistance obtained by experiment. From this, it can be seen that Arrhenius activation energy of macrocell corrosion tends to change with increase of specific concrete resistance. On the other hand, activation energy of microcell corrosion is almost constant regardless of specific concrete resistance. So there is possibility that the macrocell corrosion becomes much higher in warm temperature region, and it needs to pay attention to it. Based on the experimental result I mentioned before, the prediction of deterioration process was conducted in this study. This conceptual diagram shows the deterioration process of reinforced concrete denoted in Japan Society of Civil Engineers Specification Maintenance Edition. According to this specification, the deterioration period can be separated initiation, propagation, acceleration, and the deterioration period. Especially initiation period is highly related to diffusion coefficient, and propagation and acceleration period is related to corrosion rate. Therefore, these periods are predicted based on the experimental result, and the lifetime is calculated as the sum of initiation, propagation, and acceleration periods in this study. In the case of calculation of initiation period, the period that the chloride ion concentration reaches to 2.0 kg per cubic meter is calculated by this equation. This equation is based on the Nernst-Planck equation considering with Debye-Hückel theory and electroneutralization condition proposed by authors. In this study, this equation is improved using temperature dependency obtained before. Also, propagation period and acceleration period are calculated as shown in this slide. The corrosion quantity of propagation and deterioration period are set at 10 mg per square centimeter and 510 mg per square centimeter respectively, indicated in the literature reviews. Example of temperature profile is shown in this slide. In this calculation, monthly mean temperature used at 55 cities of lifetime prediction are calculated as shown in this table. This graph shows the lifetime of reinforced concrete in each city, and x-axis shows the annual mean temperature of each city. From this, it is predicted that the lifetime becomes almost half with 10 degrees centigrade of annual mean temperature elevation. And the lifetime of Southeast Asian country becomes 70% of the region where the average temperature is 20 degrees. We also had the exposure test in Kurihama Bay in Japan and Manila Bay in Philippines. The temperature is almost different 10 degrees centigrade. This graph shows the y-axis shows the measured value exposed to Philippines, and x-axis shows the exposed to Japan. To compare these data, the corrosion rate exposed to Philippines is higher than Kurihama Bay. And considering the Arrhenius activation energies, this Japan data can be translated to like this. When we considering the temperature effect, the both of value become the almost same. Conclusions. Chloride ion diffusivity and corrosion rate in concrete increased with temperature elevation. In addition, these phenomena can be expressed by Arrhenius theory from the viewpoint of practice. According to estimated result of lifetime exposed to several cities in severe marine environment, the lifetime of the structures in South Asian countries are estimated relatively short. Thank you for your kind attention.